Welcome to another podcast. In this episode, we're going to be taking a look at what is called the method of undetermined coefficients. This is used in order to solve a inhomogeneous equation of the form y double prime plus ay prime plus by equal f of x, where a and b are constants. The goal of this video is to find the particular solution y sub p. To help us find the general solution to the equation. The technique, or what we're going to try to do here, is look for y sub p's that replicate f of x and its derivatives. Now, I know that's sort of a strange thing to say. What do I mean by that? Let me just give you a couple of examples here. So I'm going to have a trial solution, basically a guess. My guess at the solution is going to be y sub p, and y sub p should consist of f of x and its derivatives. So, for example, if f of x is equal to an exponential, say ae to the rx, then my guess y sub p is the exact same thing, because if you take the derivative of e to the rx, you get back e to the rx, but the constant may be different. So rather than lowercase a, I have capital A representing a different constant. So if my function is forced by an exponential, then my guess is an exponential to be the solution. If my function is cosine, so let's say it's something like a cosine omega x, then you might guess that my trial solution involves cosine, and you'd be right, but it also involves sine. The reason for that is my trial solution needs to consist of f of x and its derivatives, and if you take the derivative of cosine, you produce a sine. Therefore, the best trial solution, or the best guess to start off these problems, would be cosine omega x plus b sine omega x. Notice I didn't change the frequency of the oscillation. That'll be exactly the same. And it shouldn't surprise you here that we include both sine and cosine, because you know that you can combine sines and cosines of the same frequency into just a single either cosine or sine of that frequency. All right. What if we have a polynomial? So say, for example, that we're looking at a0 plus a1x plus, let's just make it an nth order polynomial. Then the trial solution in that case will be a polynomial of the same degree with different coefficients. And so you see, in each case, we're basically going to be looking at what f of x looks like, and then to determine what our solution y sub p is going to be. And then the whole idea is we take this y sub p, plug it in, see if it works. In other words, we figure out what these constants a and b and a0 through an all have to be to make this process go. So I just want to do a small example of this to show you. Let's look at the equation. Let's give myself a little bit of room here. So I want to look at the equation y double prime plus 3y prime plus 4y equals 3x plus 2. Then what I immediately notice is that my f of x is 3x plus 2. So my trial solution should be a linear equation with arbitrary constants ax plus b. I'm going to have to find the derivative of this, which is a, and the second derivative, which is 0, because I'm going to be plugging them back into the equation. All right, once I make my substitution into the equation, y double prime is 0 plus 3 times yp prime is a plus 4 times yp is ax plus b. And all of that should equal 3x plus 2. So the idea here is I have a linear equation on the right side. I have a linear equation on the left side. Both of these together should be equal. So I need to equate coefficients. We did something similar to this when we did partial fractions back in Calculus 2. So for example, if I look at everything that has an x variable with it, then I'm just looking at 4a as the coefficient of x. And then if I look at the constant terms, I get a 3a from here and a 4b from here. So the constant term is 3a plus 4b. And altogether, that equals 3x plus 2. So if I equate coefficients now, 4a should be equal to 3, which means that a is 3/4. And 3a plus 4b, since a is 3/4, that's going to be 9/4 plus 4b should be equivalent to 2, because the constant here should be equal to the constant here, which is 2. So solving for b in this case is in the way that you would expect, would give b equal to -1/16. So that means that my particular solution is 3/4 x minus 1/16. I look back at what my trial solution was, and I've since found the value of a and the value of b. I then plug them back into y sub p, and now I have my inhomogeneous solution. So here's sort of a follow-up question to this. What is the general solution? Well, remember the general solution from the previous video is y sub h plus this solution I just found, y sub p. In order to find y sub h, I have to look at the characteristic equation, which I'll do this in a different color here. So if this is my differential equation, the characteristic equation is given by this, and this does not factor nicely. It turns out that the roots for this are equal to -3/2 plus or minus the square root of 7/2 I. I encourage you to verify that for yourself. But since those are the characteristic roots, then the homogeneous part of this problem is given by e to the -3/2 x from the real part of the root being -3/2. And then we've got a c1 cosine square root of 7/2 x, because the imaginary part is square root of 7/2, plus c2 sine of square root of 7/2 x, plus the y sub p part in red is what we just came up with as 3/4 x minus 1/16. So together, both of these form the general solution of this differential equation. One part homogeneous, one part particular, and in this lesson, we know how to solve for the particular solutions using method of undetermined coefficients. All right, thank you for watching.